No, I don't. Yeah, I'm not a TA, so I don't have like direct communication. But I believe I was in your class on Friday, and I think for sure it'll probably be done on Wednesday. I want to say because I think that's what he said was for sure by Wednesday. Yeah, before the final for sure. Because I know he was saying, he was like drowning in creating, but he was definitely going to get it done by then. Yeah. Yeah, I think the try prediction is a little more complicated. Okay, it's 11. We can go ahead and get started. My name's Cameron. This is Computer Science 1. Just make sure everybody's in the right room. Okay. The format for this is going to be a little bit different than SARC. So I'm just going to talk for a while, and then we'll have questions at the end. Can everybody hear me okay? I kind of like lost my voice on Saturday, the game. So, all right. Yes, well, I'll probably try to save like between 30 and 15 minutes at the end for like more long form questions. If anybody's like confused or needs clarification, feel free to raise your hand during the thing.
Where is that?
Where is this? I have not posted it yet because I kind of just made it recently, but I'm going to try and put it on the SARC WordPress site. And so I'll have to do that, and then you guys can download it. But it's got some blanks in it because I'm going to fill them in right now. So if you want to just take notes on the stuff that I'm doing, and then, try to do them again on the thing by yourself, maybe. That'd probably be good. Okay, so we're going to start out with dynamic memory allocation, just like a quick review. I won't say too long on this. So essentially, when you need memory, but you don't know how much you're going to need until the program is already running, you want to use dynamic memory allocation. So you have your two main functions for this are Malloc and Callek. So essentially, they do almost the same thing, where Malloc just gets you a block of memory, and that's it. And Callek does the same thing, except for it also zeroes out whatever is already there, so you don't have the garbage data there. Basically, the syntax for the two is the same, except for with Malloc, you just pass it the Sizeof function and the type of memory that you want. Then you multiply that by how many of those individual elements you want. So if you want 4 ints, you do Sizeof int times 4. Callek, you do the number that you want as one argument, comma, and then the type of data that you want. So it's essentially the same thing, except for one is 2 arguments, the other one's multiplied together. In this diagram here, we have where you have like int array, right? So you do Calloc 3, Sizeof int. So that'll get you 3 memory addresses, and they will all have zeros in them, stored in them. So like the data value that will be here will be initialized to 0. Whereas if you use Malloc, you get a single integer. This will have some type of garbage data in it. So you need to make sure that if you're, for example, if you're like summing something up, you need to set it to 0. Because obviously if you sum just some random number as the beginning, it's not going to work. Okay, moving on. Segmentation faults. That's like one of the first things you guys learned about this semester. Essentially, these are just things you have to watch out for, make sure you don't do. So there's 3 types. The first one is dereferencing an uninitialized pointer. And essentially what that means is if you create a pointer, right, like int p, star p, and then you try to change the contents at that address. So you use the star again and then p. You're trying to access p, go to where it's located, and then change the contents of it. If you try to do that to an address that was just initialized there without you giving it to it, you're more than likely going to go outside the bounds of the program that, like the space that your program has been allotted. So essentially the operating system won't let you do that, obviously, because you could do some real damage. So it'll give you a segmentation fault. The second one is if you dereference a null pointer. This is guaranteed to give you a segmentation fault every time because the null pointer points to like the 0 instruction, which is highly protected. So if you try to go to a pointer that's been set to null, it'll give you a segmentation fault. The last one is if you access an array out of bounds. So this one also has a chance to do it. It's generally a bad idea. But essentially, if you go outside the bounds of the array and you hit something that's not a good thing to hit, it's going to give you a segmentation fault. It's possible to go out of bounds. So for example, if you had this array here, you give it 4. So these 4 here. Oh, sorry. So these 4 here are your the 4 memory addresses that it gave you. So if you were to go to array 4, it's going to go right here. And then that's going to cause you a problem because it's not actually reserved memory that was given to you. Okay, now come over here. So memory leaks is kind of a similar concept. It's just something you got to avoid doing. Essentially what happens is, for example, if you declare this int array here, again, Calloc 3, so you're getting a 3 element array, and then you declare another pointer here, just a single integer. Then you come down here and you set another pointer and you set it equal to array. Right? The element that P was originally pointing to is still out there and it's still reserved. So if you're not careful, especially if you have some big arrays and you start removing the pointers to them, those arrays are still out there just like locked, but you have no way of accessing them. So you're just like sort of saving a bunch of space that's reserved and can't be used, but then you can't use it either. So if you just made a new array every time and didn't free it, you would end up with just a bunch of just huge blocks in your heap that are just not usable, and that's going to slow your program down because it's going to take longer to find new memory every time. So I didn't write it down here, I just realized, but the free function is how you usually deal with that. So whenever you have a pointer to anything, right, when you're done with that pointer, you're going to free it so that the program knows, okay, we don't need this anymore, we can let it go back to the heap where we can look for it again. You got to be careful with this though, because if you free something that's already been freed, it'll give you like a really nasty crash, which I'm sure some of you have seen when you were doing the smart arrays, where it'll essentially like give you this huge like trace of like corrupted memory and all that stuff. So got to watch out for that. Okay. Let's see. Big O, recurrence relations, and summations. So we're going to start out with like the basic closed forms, like the rules that you use to evaluate simple summations. And then we're going to move on to somewhat complicated recurrence relation. It's not too bad, but we're going to skip to that. So with this first one here, essentially like the first rule that this is demonstrating, right, is if you have the summation of some constant times, oh, yeah, sorry. Okay. So if you have the summation of some constant times I, right, you can pull that constant out. Times anything really, as long as whatever the constant isn't changing with the index of the summation, you can pull it out. So you can have 5 times the summation from I equals 0 to n of I. Okay, so that's the first rule. And then the second rule is if you have the summation of just I left inside, right, you can take from I to 0 to n is equal to n times n plus 1 over 2. Now this is just like something you got to memorize, right? It's essentially whenever you have the summation. Now this doesn't change whether it's I equals 0 or I equals 1, because if you add a 0 at the beginning, it's not going to make a difference in terms of the actual answer. So then you have your 5 coming back over here, right? So it's 5 times this. So this would be the closed form for this summation. Okay. Now if we look at this one, it's kind of the same thing. Oh, okay. It's kind of the same thing, except for this one, you have something else you can do. So you can take the summation from I equals 1 to n, and you can pull the 5 out and leave a 1 inside. And then you can add that to the summation of 3 times I from I equals 1 to n. Okay, so does everybody follow how that worked? Okay. So now you evaluate both of them separately. So what is the value from I equals 1 to n? So essentially what you're doing, right, is you're counting 1 and adding it up n times. Because if you go from 1 to n, you're going to do it n times. So if you add 1 n times, it's going to be equal to n. So this one's just going to be 5 times n. And you're going to add that one over here. And what did we say? We said the sum from either 0 or 1 to n of I is going to be n times n plus 1 over 2. So this is your closed form for the second one here. Okay, the third one is going to be a geometric sum. So this is going to take a little bit more work, but it won't be too bad. So we know that if we have the sum from I equals 1 to n of 1/3 to the I, then that sum is essentially going to be equal to 1/3 to the 1 plus 1/3 to the 2. I should put parentheses around these. All right, plus dot 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 plus 1/3 to the n. Okay. Now, what we can do, usually the trick that you do with these is you multiply your sum here, your s, by whatever the base is in your summation. So we'll have 1/3 s is equal to 1/3 to the 2 plus 1/3 to the 3 plus dot 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 plus 1/3 to the n plus 1. Okay? Now, what we're going to do is, you can sort of do this either way, but I think what I'm going to do is I'm going to take s and subtract 1/3 s. So that's going to give us s minus 1/3 s. And then that's going to be equal to this minus this. So if we take these like this and we cross them out, you know, as they lie, essentially this is going to be crossed out with some n over here. And what we're going to have left is we're going to have 1/3 to the 1, right? And then on the end, we're subtracting a 1/3 to the n plus 1. Now, what we're going to do is we're going to take this and simplify this. So we're going to get 2/3 s is equal to 1/3, we don't need to the 1 power, minus 1/3 to the n plus 1. Now we can multiply this side by the reciprocal of 2/3, so 3/2. And so what we'll get is s is equal to 3/2 times 1/3 minus 1/3 to the n plus 1. Now, you can multiply this in, and you can bring it down to s equals 1/2 right here, and then you multiply this in, and you're going to get a, let's see, you can just subtract it like this, 1/2 times 1/3 to the n. So that's your closed form for that geometric sum. So essentially that's establishing the, that's establishing the trick that you got to do, and there's a good chance that you may see something like this on your final, because a lot of the recurrence relations that he does tend to be something that involves a geometric sum, especially on the final, because the easier ones tend to not, right? They just go straight through and you can get it. But if he puts something like that on there, you're going to need to know this trick for basically any geometric sum. Okay. So now we're going to do this recurrence relation. We're going to use iterative substitution. So we have our recurrence relation here, and then we have our base case. The first thing we're going to do is we're going to say that we're going to take t of n over 2, and we're going to figure out what that is. So we're going to start right here, and we're going to say it's going to be 4 times t of n over 2. So what's t of n over 2? So t of n over 2 should be 4t of n over 8. And then we're going to put plus n over 2 plus c1. Okay? And then from there, we're going to have the plus n on the end and the plus c1. Okay, now if we simplify this, we're going to get 16 t of n over 4. I'm sorry, not t of n over 8. This should be t of n over 4. So we're going to get 16 t of n over 4. And then we're going to have plus 2n plus n plus 4c1 plus c1. Okay, now you can combine these terms, but actually it will probably be easier to figure out what the pattern is if you leave them separated for now, because if you try to combine them, it'll be harder to see like what the pattern of each increasing step is going to be in terms of n and c1. Okay, so now we're going to take t of n over 4, and we're going to try to figure out what t of n over 4 is. So we're going to have 16 times t of n over 4. So what's t of n over 4? That's going to be 4t of n over 8. Okay, and then we're going to have plus n over 4 plus c1. And then we're going to have plus 2n plus n plus 4c1 plus c1. Okay, now simplifying this, we're going to have 16 times 4, so we're going to have 64 t of n over 8, right? And then we're going to have 4n plus 16 c1 plus 2n plus n plus 4 c1 plus c1. Okay. Now, going from here, we're going to take it one more step just to make sure that we've got the pattern down. So we need t of n over 8. So we're going to say 64, and then t of n over 8 should be equal to 4t of n over 16. And then we're going to have plus n over 8, then plus c1. Okay, so then from there we need to add, and I'm going to flip these terms around a little bit so that the pattern might be a little more obvious. So we'll have plus 4n plus 2n plus n, and then plus 16c1 plus 4c1 plus c1. Okay? Okay, so now if we simplify this, we're going to get 256 t of n over 16 plus 8n plus 64c1. 64c1 plus 4n plus 2n plus n plus 16c1 plus 4c1 plus c1. Okay. Now, what we're going to do is we're going to look for the pattern here, right? So in general, what does it look like we have? So for here, we're going to say, we can just say k is 1. So we had one iteration. And then when we come down here, k is 2. And then when we come down here, k is 3. Right? And then we'll come down here and we'll say this is k equals 4. Okay? So essentially, we want to look for a pattern in terms of k. So we want to say that this right here, 256, we can write that as 4 to the k. So in general, we have 4 to the k t of n over 2 to the k, right? So that's the usual pattern when you divide by 2, is it just ends up being n over 2 to the k. And then after that, if we look over here, we can see 8n, then 4n, then 2n, then n, right? And we have, so essentially we can write this as a summation. And what this summation will be is from I equals 0 to k minus 1 of 2 to the I times n. Does everybody follow how that summation works? So if you have I equals, I equals 0. So you have I is 0, it's 2 to the 0, which is 1. So you have the 1n, which is right here. And then if you do 2 to the 1, you get the 2n, 2 to the 2, you get the 4n, 2 to the 3, you get the 8n. And then that's the total n terms for the fourth iteration. Okay? So then the last one is going to be another summation. So we're going to get I equals 0 to k minus 1 of 4 to the I times c1. Okay? So now we can rewrite this a little bit, and we can get 4, or I'm sorry, not 4. We can get 2 to the 2k, right? T of n over 2 to the k. And it'll become a little more clear why I did that in a second. Plus the summations that we had above. So plus the summation from I equals 0 to k minus 1 of 2 to the I times n, plus the summation from I equals 0 to k minus 1 of 4 to the I. Actually, we're going to rewrite this one too. No, we won't. We'll leave it alone. 4 to the I, c1. Okay. So now, we know that for our base case up here, that t of 1 is equal to c2, right? So what we need to do is we need to say that n over 2 to the k needs to equal 1. So when n over 2 to the k equals 1, we know that n equals 2 to the k, approximately. And that's assuming that Rn is a power of 2, but we're just going to do that because it makes it a little easier. And then the last thing we know is that k is equal to the log base 2 of n. Okay, so now what we're going to do is we're going to rewrite our summation in terms of these things that these facts that we just know when we're going to hit our base case. So we can say that instead of 4 to the 2k, we can write it as 2 to the 2 log of n, log base 2 of n, okay? And then we can say times t of n over n, because we're replacing 2 to the k with n, right? So that's essentially just going to become 1. And then we have our summations over here. So we're going to say from I equals 0 to k minus 1. And we can pull the n outside of this from the summation up here. We can pull this n out. So we're going to, if we pull the n out here, because n is going to be constant, right, in terms of the summation. The only thing that's changing is I. So we can pull the n out, and then we'll have the summation should be k minus 1, not ki. And then from here, we're going to have 2 to the I, and then plus the summation from I equals 0 to k minus 1. We can pull the c1 out, and we'll get 4 to the I. Okay. Now I'm going to pull another piece of paper out over here, and we're going to work out these two summations, which will be very similar to the previous ones, and then we'll come back and finish it out right here. So we had the summation. So we have the summation from I equals 0 to k minus 1, n times 2 to the I. Okay. So now what we're going to do is we're going to do the same trick we did before. So we're going to say the sum is equal to 2 to the 0 plus 2 to the 1 plus dot 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 plus 2 to the k minus 1, right? So now if we say 2s should be equal to 2 to the 1 plus 2 to the 2 plus dot 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 plus 2 to the k. Now if we take 2s and we subtract s, we're going to get 2s minus s, and we're going to get this. So essentially it should be 2 to the k, right? That'll be the only thing that'll be left over here. If we cross these out, and then we cross this out like that, we'll have 2 to the k over here minus 2 to the 0, which is just 1. Right? So we'll have 2 to the k minus 1. So then 2s minus s is just going to be s, obviously. So we'll have s is equal to 2 to the k minus 1. Now, if we look at the other summation that we had over here, this 4 to the I, it's essentially going to work, it's essentially going to work out to be the same thing, except for it'll just be 4 to the k minus 1, because the process will be exactly the same. So we're going to skip doing that, and we're just going to say that this is equal to, first of all, we're going to do a simplification right here. 2 to the 2 log base 2 of n is essentially just n squared. Because the 2 and the log base 2 cancel, and it brings the n down, and then it's still squared. So you're just going to have n to the squared that's still left up there. Does everybody follow that? So it'll be equal to n squared t of 1, right? Plus, we had n outside the summation there, so it'll be n times 2 to the k, we can replace with n times n minus 1, right? And then we can do the same thing here with this last summation, except for our answer was plus 4 to the k minus 1, right? So now that one's a little bit different, because obviously you can't just replace the 4 to the k with n. So what you have to do, and then this should be times c1. Times c1. So now if we bring it down here, we can do one final simplification, and we can say n squared t of 1. But what is t of 1? It's c2, based on our base case up here. So we'll say n squared c2. Then we're going to have plus n squared minus n, and that's just simplifying this right here. So n squared c2 plus n squared minus n plus And then if we take this 4 to the k minus 1 and we make it 2 to the 2k minus 1, we'll have 2 to the 2k minus 1. And what we can do from here, this is all multiplied by c1. And then from here, what we can do is we can say n squared c2 plus n squared minus n plus, if we replace the 2 to the k with n, it'll be another n squared. So n squared minus 1, and we multiply it in, it'll be c1 n squared minus c1. Okay, so then if you take this polynomial, this is what your t of n is equal to, right? So we have t of n is equal to this. We take the big O of this, it's O n squared. Okay, does everybody follow that? As long as it's a little bit long, but I definitely think there's a good chance that at least one of the wildcard problem might be something like this. And it's also, for everybody that's a CS major, it's definitely going to be on the foundation exam, something this difficult. Okay, we can go back to the easier stuff now. Okay, so we're going to start out, we'll just talk a little bit about sorting algorithms. So these are the n squared sorts. So you have bubble sort, insertion sort, and selection sort. So the best case runtime for bubble and insertion is order n. That's fairly obvious, right? If your array is already sorted, it's going to make one pass, realize that it's sorted, and then it'll be done. Selection sort's a little bit different because it doesn't actually check to see usually if the array is sorted. So what it's going to do is it's just going to find the lowest element and just swap it with itself. And then it'll find the next lowest element, swap it with itself, find that. So it'll end up passing through the array and plus n minus 1 plus n minus 2. It'll do the whole passes anyway, so it'll end up being n squared. Obviously, the worst case for all of them is n squared because if it's really badly sorted, there won't be any. It'll essentially do all the passes no matter what. So it'll have to pass through the array n times, which n times n is n squared. So we're going to do one pass of bubble sort here, and then we're just going to write what the array is going to look like after that. So we start out with 17, right? 17 is bigger than 3, so it'll move along. 17 is then bigger than 14, so it'll move along. 17 is bigger than 11, so it'll move along. 17 is bigger than 9, so it'll move along. So 17 is going to end up right here. Then we're going to move to 20. 20 is bigger than 18, so it'll move along. 20 is not bigger than 38, so 20 is going to end up right here. 38 will move, and we'll end up like that. So it'll be 1, 27, 38. And if we come back over here, we move the 17 over, so it'll be 3, 14, 11, 9. And then from the 17, we move to the 18 over, so it'll be 18. Okay, now I'm going to do selection sort. So essentially, selection sort, I mean, this is pretty simple, but you're just going to look through the array and you're going to find the lowest element. So right here, the lowest element we've seen is 17. Now the lowest element we've seen is 3. It's going to stay 3 all the way until we get over to this 1. Now we've seen a 1, so the 1's the lowest element we're going to see. We're going to go over here. Now we're going to take this 1 and we're going to swap it with 17. And that's one pass of selection sort. So you're going to have 1 right here. Oh, there we go. Okay, so you're going to have 1 here, and it's just going to be 3, 14, 11, 9, 20, 18, 38, 17, and 27. Okay, and then the last one is insertion sort. So essentially what you're going to do is you're going to take this element here and you're going to say, okay, so 17 is sorted within itself, right? Then you're going to look at 3 and you're going to pull it down, and then you're going to put it into the sorted partition, and you're going to say, does it go on the left or right of 17? Obviously it goes on the left, so it's just going to be 3, 17, 14, 11, 9, 20, 18, 38, 1, and 27. Okay, and then obviously these two right here are considered sorted, and then you'll just keep picking the next one and putting it in where it belongs from there. I'm going to talk about quicksort and merge sort real quick. The Best case for quicksort is going to be n log n. The worst case is going to be n squared, and that's if the array is also sorted. The average case obviously being n log n. Merge sort is n log n for all three, best case, worst case, and average case. We're not going to look at merge sort because honestly, doing one pass of merge sort is kind of easy because it's just splitting it in half. There isn't really any work done until you get to the bottom, and then there's way too much work to do. So we're just going to start with quicksort. So essentially what you're going to do is usually what you would do is you would do the median of 3 or the median of 5, which is essentially you pick 3 or 5 random elements from your array, and then you pick the median value from either that 3 or that 5, and that's how you would pick your pivot. But for our purposes, we're just going to pick the first element because it makes it a little bit easier. So we're going to say that this is the pivot, and then we're going to have a right pointer right here and a left pointer right here. So we're going to say this is the right pointer, and this is the left pointer. Okay, so we're going to keep moving along the right pointer until we find something that is bigger than our pivot. And we're going to keep moving along our left pointer until we find something that's smaller than our pivot. So 3 is not bigger than our pivot, so we'll move along here, and then we'll have the right pointer right here. And then this is not smaller than our pivot, so we're going to move this one along over here. And then we're going to keep going. So now this is smaller than our pivot, right? So our left pointer is going to stop. So our right pointer is going to keep moving, it's going to keep moving, it's going to keep moving, and it's going to hit 20. So our right pointer is now bigger than our pivot. So we're going to swap these two elements. So we're going to swap 20 and 1. So that means that we're going to put 1 here, and we're going to put 20 here. Okay. Then the pointers are going to keep moving. So we're going to say that the right pointer is still looking for something bigger, so it finds something at the next element. And then now it's going to wait here. The left pointer is looking for something smaller. The left pointer is looking for something smaller, so it's not going to find it. And it's going to swap over right here. Right? Now, once they swap, right, they've switched positions, you're going to take your pivot, and you're going to take your right pointer, and you're going to swap those. So now we're going to put 17 here. We're going to put 18 here. Then we're just going to copy the rest of this down. And we're going to say, now usually what you would do here at this point is you would make the recursive call for quicksort, which would take the left partition on the left side of your pivot, and you would take the right partition on the right side of your pivot, and you would call quicksort on both of those. So you essentially are doing the same process again. You're picking another pivot, you're picking another pivot, you're doing it twice, and you keep moving down until you hit your base cases, which you then take it from there and you take the array back up and you put it all together, and then that's the it's the algorithm. Okay, let's see. So now we're going to look at binary trees and AVL trees. So we're going to draw out a tree here real quick, and then 22, 18. It's a little blurry, but 4, 20, 19, 35, and 100.
What's the number?
Oh, sorry. Let's make it a little bigger. Say 22. Yeah. 35, and then 100. Okay. So from here, we're going to do the pre-order traversal, post-order traversal, and the in-order traversal. So the pre-order traversal, the way you do that is, obviously, as pre-order sort of insinuates, you visit it, and then you print out itself, and then you do the other ones. So it's it's before. So we're going to do 22, and then we're going to call left and right. So it's going to go left first, so it's going to say 18, and then it's going to call 4. Then 4 is both of their children are null, so it's going to come back up. Now it's going to hit the right call, so it's going to be 20. And then we're going to call 20's left, so it'll be 19. And then from there, we're going to go back up, back up. We'll call the right child from 22, so that'll be 35. And then you call the other child, the right child, and it'll be 100. Okay, so now the post-order traversal is similar, except for you call it after you've visited both of its children. So the first thing that you're going to do in the post-order is you're going to call left, and then you're going to call left again. 4 will call on both of its children, but they're null, so it'll go back up. So now we're going to call 4, or print 4. And then 4 is going to go back up to here. It'll have called it on the right, and it'll call left, so 19. Then from 19, we're going to go back up. And since we visited, well, we're going to call it on the left of 20. Then since we visited both of 20's children, we can print 20. Now we can go back up, and since we visited both 4 and 20, we can print 18. Okay, so now from 18, we're going to go back down the right. Down the right, we're going to say, okay, we visited both of 100 children, so we can print 100. Then we're going to go back up. We've visited both 35 children, so we can print 35. And then lastly, we can print 22. Okay? Now, the in-order traversal is actually even simpler because essentially the way you code it up, you put it between the two calls. But when you're doing it from just a tree written like this, you can just write the numbers in numerical order, sorted order, and that's pretty much it. So we'll do 4, 18, 19, 20, 22, 35, 100. So that's the 3 traversals of a tree like this. Everybody still following with that? Okay. Now, AVL tree insertion. Okay, I'm going to try to do this without screwing it up. It's somewhere in my writing, but we'll see. So I'm going to start right here, 50, 25, 12. So actually, before I do this, okay, we're going to talk about the 2 properties that an AVL tree, actually the 1 property that an AVL tree has to have. So usually it's calculated using the balance factor. So you have to have a proper AVL tree, it's got to have a balance factor of either -1, 0, or 1. And essentially the way that that's calculated is you take the height of the left subtree, and then you subtract the height of the right subtree. So if the right subtree's height is 1 higher than the left subtree of a particular node, then that's considered okay. If they're the same, that's ideal. And then if it's the other way around and the left subtree's height is 1 higher than the right, that would be a +1 factor, and that's also okay. So it becomes a problem when you get a balance factor of either 2 or -2, and that's when rotations start. So we'll see an example of that right here. Okay, so what we're going to do is we're going to insert 67. So when we do that, we're going to get, oh, that's too small. No, well, 50, 25, 12, 35. Here we're going to get 70, 65, 67, and then 90. Okay, so from that insertion, we can look at this node that we just inserted. Its balance factor is obviously 0 because it doesn't have any children on either side. Now 65, the left subtree height minus the right subtree height, so the difference is going to be -1, right, because it's 1 right heavy. Now if we go back up here, for node number 70, it's going to be the difference between the left and the right. So because it's 1 left heavy, the balance factor is going to be 1. And then if we go back up to the root, it's going to be 1 right heavy because it's 3 minus, or 2 minus 3, so it'll be -1. Okay. Now we're going to insert 66. So we'll go over here. And we'll say 50, 25, 12, 35, 70, 65, and 90. Okay, so from here, we need to insert 66, or sorry, we need to put a 67 first. So we're gonna have 67, and then from here, we'll have a 66. So now, obviously, this is gonna cause a problem because the balance factor is gonna be 2 or -2, and we'll see in a second. So the balance factor here is going to be 0, obviously. And the balance factor here is going to be +1. It's right heavy, or left heavy. This one is going to be a balance factor of -2. And the balance factor up here is going to be -2. Or, I'm sorry, 2. And then the balance factor up here is going to be -2. Okay. So now we're going to perform a rotation. So obviously the problem here is at 65, but because 65's balance factor and 67's balance factor do not match, we're going to have to perform a double rotation. So what we're going to do first is we're going to make a right rotation here, and then we're going to make a left rotation at 65. So what that'll end up looking like is we'll have 50 here, 25, let's see, 12, 35, 70. So when we make, our 90 will stay the same. And then when we make the right rotation, it'll end up being 65, 66, 67. And then we're going to rotate backwards this way. So what'll end up happening is you'll have 66 here. You'll have 65 here. You'll have 67 here. Everybody follow? So that was after both. So do you want me to draw the other one real quick?
Sure.
Okay. So essentially, I'll just draw it right here. So when you have the right rotation here, you're going to get the 66 coming up, right? You're going to get the 66 right here.
Gotcha.
And then the 67 is going to come down over here. Yeah, the 67 is going to come down over here. So you'll get rid of this node entirely. And your 67 node slides over. Right, so then now when you take this and you perform the left rotation at 65, the 66 is going to come up, the 65 drops down, and the 67 stays on the right. So now you've got a balanced AVL tree. So the balance factor is going to be 1, but it won't be -2 or +2. I'm sorry, it'll be -1. So yeah, so we have a balance factor here of 0, we have a balance factor here of 0. This one's also 0. This one's going to be +1. And then up here will also be +1. So that's good for now. Okay, now we can do a deletion. So we're going to delete 65 from this tree. And then we're going to delete 90. So we're going to start with, I'm sorry, not 90. We're going to delete 65. So if we delete 65, it just goes away, right, because it has no children, so 65 is gone. So now, if we want to delete, let's see, what would be a good one to delete? If we want to delete 70, what is the process for deleting a node that has children? So if you want to delete 70, what you're going to do, so this was deleting 65 since it was a root, nothing happened, you just got rid of it. Now, if you want to delete 70, you're going to have 50, 25, 12, 35. Now, we deleted 70, so we're going to go to the bottom rightmost node in the left subtree. So we're going to get 67. We're going to pull up 67. And then this one's going to go away here. And we're going to say 66 is here, 90 is here. Now, is the tree still balanced? Yeah, right. So that works out fine as well. Okay, moving on from there. Does everybody get that? Trees, insertions, deletions. I mean, obviously the insertions for binary search trees are pretty basic. So I didn't go over an example of that, but just move left, move right, depending on comparison of what you're inserting. Okay, so now we're going to do tries. I don't know. I feel like this is getting like more blurry. Is that just? Okay, let's try and move it over here. It's like getting. Well, can everybody at least? It says tries, heaps, and hash tables. So we're going to insert the sentence, I really like pie and race cars, into our try. So this may take me a minute to draw, but I promise it will be amazing. So first we're going to insert I. We're going to put a 1 here because there's one word I. Then we're going to put really. So we'll put the R here. Then we're going to put E, A, L, L, Y. So I really like, we'll bring the L off here. So I really like, now we need pi. So we'll put a P here, I, E. Okay, I'm forgetting the ones at the end. So you got to make sure you update the count at the end of your words. So I really like pi, and, so we'll put an A, N, D. For here, put a 1 there. And then race cars. So we'll have R, A, C, E, C, A, R, S. So I really like race cars. Okay. So now, so that was insertion, right? You just add a node. Now notice how I didn't make 2 R nodes for really and race cars because R is shared. So you just have the single R node, and then from R you split off to really with RE and then race with RA. So insertion's pretty simple. Now deletion has basically 2 simple rules. So if I want to delete race cars, for example, right? I go to the end of race cars. I find the end. So I say, okay. So I'm going to decrement the count by 1. Right? So that's going to become a 0. So then I check if the node I'm currently on, does it have a count of 0? Yes. Does it have any children? No. So I delete it. Then I move back up 1. Here, does this have any children now that this one's deleted? No. Does it have a count of 0? Implicitly, all the ones that I didn't put a count in are a count of 0, so you delete it. You do the same thing for all of these nodes, right? Then you come up here to the R, and you're going, this is all deleted, and it does have a count of 0, but it still has, yeah. Right. So you're keeping track of the previous one free. So it usually would probably be done recursively, so you don't lose track of what you're going back up. But, so you get up here to R, and it does have a count of 0, but it has another child. So that's how you know to stop. Because otherwise, because you don't want to delete the R in race cars, because then you wouldn't have a way to get to the rest of really. So usually we say that the insertion, deletion, and search operations are order k, where k is like the length of the string that you're inserting, which is pretty fast, usually, because strings are usually not very long in comparison with how many data elements you would have. Okay, so let's see. Moving on from there, okay, we're going to do a heap. So we'll do a min heap because I think that's the one that you guys look at in CS1. So we're going to start with, let's see, 1, 17, 24, 58, 19, and 27. Okay. So usually with a heap, you have two properties, right? So the heap has to be complete, and it has to have all of the children, well, with a min heap specifically, all of the children must be greater than the parents. The values of the children must be greater than the parents. So essentially, as you're moving up the tree, you're getting from big to small, and as you're moving, you're filling in from left to right, is essentially what you're doing. So usually the actual representation of a tree or a heap is not in the same way with nodes like it is with a binary search tree or an AVL tree. You're going to use an array. And essentially the way you fill the array in is like this. So you have, let's see, how many elements do we have? 1, 2, 3, 4, 5, 6. So if you have 6 elements, you're going to start out with your first element that's at the root, and you're going to put 1. And your second element is going to be its left child, so 17. And the right child, so that'll be 19. And then you move to the third row, and you just kind of move across like that. So you're going to have 19, 24, 58, 27, right? And then the rest of this is open for insertion. So the way that you move around this is if you're looking at a node, and for example, let's say you want to find the left child of node 1. So you're at index 0. So you would write, so the left child is equal to 2i plus 1. That's the formula. So if you're at, oh, yeah, sorry. It's like not enough space. All right. So this is index 0, 1, 2, 3, 4, 5, right? So if you're at index 0 and you want to find its left child, you're going to put a 0 in for I. You add 1. It's going to go to 1. So 17 is 1's left child. And then for the right child, the formula is 2i plus 2. So if you're at index 1 again, or index 0 at node 1, then you're going to add 2 to 2 times 0, which will be 2, and that's the right child. So if you want to try it with 17, for example, 17 is in index 1, so it should be, its left child should be at 2 times 1 plus 1, which should be 3. So 24 is its left child, and then its right child should be at 2 times 1 plus 2, which should be 4. 58 is in the 4th index. Everybody got that? Okay. So now the way that we insert is we keep track of where the last index in the array is, which is also going to be the bottom, well, it's going to be the node that it fills in the row next from left to right in the lowest leaf level. So if we want to insert 10, for example, we will add a 10 right here, which will basically put a 10 right there, right? Now we have to do the percolating up operation. So we look and we say, okay, is 10 greater than 19, which is what we want for our heap? No, so we're going to swap those two. So this is going to, I'll redraw the tree down here. So this is going to become 1, 17, put this right here, 24, 58. Then we're going to have the 10 here, which will stay here because 10 is now bigger than 1, so it can't percolate up any more than that. And then we're going to have the 27 still here. And we're going to have the 19 here. Okay? So now our tree has both the, our heap has both the properties that we want. So all the elements that are children are bigger than their parents, and the tree is still complete. So now we have this here, and so our next index here will be 7, which would, our next child would go right here if we had another child, or another element to insert. Now, for deletion, there's something special about heaps, right? So you cannot just delete any element. There's only one element that you can delete, and that's the root. Because it just, the way it's set up, it just wouldn't make any sense to delete arbitrary elements. So essentially, you're deleting the one element at the root, and then you're just going to bring the last node in there, and it's going to percolate down. So if we delete 1, for example, we'll have a tree, and we're going to replace it with 10. Because, or no, I'm sorry, we're going to replace it with 19. And then 19 will percolate down, so 10 will move up, and then 19 will be left. So it'll be, if we have our tree here, we'll replace it with 19. We'll get 17, 24, 58, and this is still 10, and this is 27, and this child is gone. So we move the 19 up here. So now the 19 is going to percolate down, so we're going to look at the two children, whichever one is less, we're going to move the 19, swap the 19 with whichever two of its children is less. So 19 swaps with 10, and we'll get this tree right here. Right, okay. 10, 17, 24, 58, 19, 27. Okay, so now we're back to a proper heap where the elements, the children elements are all greater than their parents, and the tree is still complete. So that's how the deletion works. Questions? Okay. So now for this, the runtime, we're looking at log n for insertion, log n for deletion, and then like a special application, and this may also come up on either the final or the foundation exam, is heap sort. So essentially the way it works is, if you take all your elements, right, and you put them in a heap, every time the node that's at the root is going to be the lowest element, right? Because that's how a min heap works, is whatever's at the root is the least element. So if you put all of your elements in the heap, that'll be an n log n operation. If every insertion is log n and there's n elements, you're going to have an n log n runtime to put them all in the heap. And then from there, if you take every element out of the heap in order, right, you're going to end up, and you put it in an array or print it out, they'll come out from least to greatest, because every time you print something or pull something out of the heap, it's going to be the lowest element that's in the heap. So in our example here, if we pulled out 1, then we would pull out 10, then we would pull out 17, then we pull out 19, and so it would end up being sorted. So that's going to be a plus n, but if you have n log n plus n, the big O for that's going to be order n log n. So that's an alternative to like quick sort and merge sort for really fast sorts, but the downside is obviously you have to code up an entire heap implementation to do your sorting. Okay. So now we're going to do hash tables. So essentially, when you need a really quick lookup for your data, this is when the hash function comes in handy. So you're going to have, let's say you have a string, right, that you want to insert. You have cake. Okay. Oh, there we go. You have cake. So then you put it in your hash function, right? And so I know, I think Dr. Smolensky says it's just a magical black box that we don't look at. So cake goes in, right, and you get a hash value out of that. So the hash value is going to be modded by your table size. So it'll be a number on the range of 0 to table size -1. So however many boxes you have in your array or whatever you're storing it in. So in our example here, we get a 7 out for cake, right? So it goes to 7, and it puts cake there. So that's going to be an order 1 operation, right? Or I guess an order k operation for string specifically, because it's going to be some operation on the length of your string. So now that cake's here, right, we can rehash cake if we want to find it, and it should give us, that's one of the key characteristics of the hash function, it has to get you the same value every time that you hash the same thing. And it also wants to do as good as possible to avoid giving you the same value for 2 different things. Now, obviously, that's not possible, but it tries to do the best it can based on what data you might be putting in, different things. So there's different hash functions for different scenarios, but they're pretty complicated mathematically, so they're a black box. So we're going to talk about the 3 collision handling techniques. So first would be linear probing. So we're going to switch to integers because it just makes it a little bit easier. So if you have, let's say you wanted to insert, I don't know, 25, right? And we get a hash of 3. So that's the same as 11. So what linear probing will do is it'll go to 3, and it'll say, okay, that's taken. So now I'm going to skip to 4, and it'll say, oh, okay, that's taken. Then it's going to go to 5. Oh, okay, so that one's open, so we're going to put it here. And then what'll happen is when you go for the lookup, it's going to do the exact same thing. It's going to go to 3, and it's going to go, oh, okay, that's not 25. It's going to move to 4, and it's going to go, oh, that's not 25. Then it'll move to 5, and it'll eventually find it. So the runtime is not going to always be order 1, but on average, it's going to be very close to order 1 if you set your table up and use these probing techniques properly. So the second one is going to be quadratic probing. So it does something kind of similar. So it'll jump to 3 with our 25 example, and it'll say, okay, is there space here? But then instead of going to the next one, it's going to go to, so it's going to go to 2 to the 0. So that's going to jump 1 space, and it's going to check here. So this is not going to work. And then it's going to jump 2 to the 1. So it's going to jump 2 spaces, and it's still not going to work. So then it's going to jump 2 to the 2, which is going to be 4 spaces. So 1, 2, 3, 4. So it's going to end up here. Now, that's what's called quadratic probing, right? Because it's jumping in terms of like x squared, essentially. Now, there's a couple things that are important to know about quadratic probing, which is it's generally better than linear probing if you do 2 things. One of those things is that your table size needs to always be a prime number, and it needs to be always at least half empty. So you have to have, if you have, I don't know, 13 elements, right? You want to multiply that by 2, so you're going to get 26, and then you want to round that up to the nearest prime number. So you're going to take however many elements you're going to have, multiply by 2, and then round up to the next prime number. So that's what you always want your table size to be. So if you so you need to keep track of how big your table size is. If you insert an element, and it ever gets to the point where the table size is, or that element, the number of elements in the array is greater than the table size over 2, then you have to, usually the process you would do is you just double the table size and round up again. So every time, and also when you do this, you have to rehash everything, every single element. And the reason for that is, if you double this table size, it's going to become really crowded here because let's say for example, this is pretty close. This would have pushed it over the point of being half full. If you double this table size and you go all the way up to 20, right, it's going to go off over here. But the problem is all of your elements will still be over here, so there'll be a lot of collisions, essentially, because it's not as spread out as it could be. So you want to rehash all your values. Not to mention, the function won't give you the same thing because you're modding by a new number. So like it won't give you 3 for 25 anymore because you're going to be modding by 20, not by 10. All right, and then separate chaining is kind of a little bit of a different thing, and I personally think it's the best choice. So essentially what it would do is when you insert an element, so you would have your 3 here, but instead of this, you would have a pointer to a linked list. So you'll have 3 like this. Here, you'll have 11. Here, you'll have 9. Here you'll have 18, 100, 27. Okay, so then if you want to insert the element 25, and it's going to go to index 3, instead of doing all that jumping around and looking, it's just going to add another element to the linked list. 25. It's kind of small, sorry, but Yeah, so it'll just add another element to the end of the linked list. So as long as your hash function is doing a decent job of avoiding collisions, your separate chains will not get very long, so it'll be very close to order 1 runtime to do insertion. Because the likelihood of getting like multiple collisions on the same thing instead of like a collision on 1, a collision on 3, and so everything's like 2, for example, that is usually what it's going to end up being, assuming your hash function is working properly. So as I mentioned before, the important factors for the quadratic probing is prime, table size, and array always half empty. So if you have those two things, your quadratic probing will never get stuck in a loop, and it'll generally be better than linear probing. Okay, let's see. What are we doing on time? So I skipped a couple things because I was trying to get through the most important stuff first. So we can go back and do bitwise operators, stacks, queues. What do you guys think? Do you guys want to do stacks and queues, or do you want to start with bitwise? And okay. All right, so we'll do some of that here, and then we can do some wildcard stuff, and then we'll go to questions. Does that sound good? Okay. Let's see. So we're going to have, okay, I'll just pull some examples from the his pages here, and we'll talk about them. So as far as bitwise operators go, you guys, how many of you are in or have been through like discrete or computer logic, or most of you? Okay. So essentially, the way the bitwise operators work is kind of the way that like Boolean logic works in general. If you have, for example, like let's say the binary number, or we'll start with integers, right? So if we have like 12, then in binary that's going to be 1, 1. It'll be 8 plus 4, so 8, 4, 0, 0, right? And then there'll be a bunch of zeros off to the left. So the way, and you know, the way it works is you've got 2 to the third plus 2 to the second plus 2 to the first plus 2 to the 0, and then your numbers here are multiplied in front of it, right? So that's how binary works. So that's, but when you do a bitwise operator, so let's say you have 12, right? And then you have, I don't know, 8. So you'll have something like 8 here, and then its representation is going to be 1, 0, 0, 0. So the first operation we'll do is you can do AND. So the way AND is represented is with the single ampersand instead of the double one, like it is in the Boolean logic. So can I draw an ampersand? Oh, I can't. Okay, not too bad. So if you have 8 ampersand 12, right? What you're going to do is you're going to do the AND operation on these bit by bit. So what is 0 and 0? It's going to be 0, right? So it'll be 0. Then 0 and 0 is 0. 1 and 0 is 0. 1 and 1 is 1, right? So you're going to get 8 back out because when you AND them together, it's bit by bit. So then we can do the same thing with OR. So the OR is going to be 8 or 12. So you use the single, I don't know what that key is called, like the line. And it's the same as the OR for like logic operations, but you just use a single one instead of the double. So 8 or 12 would be, so what's 0 or 0? That's going to be 0. 0 or 0 is 0. 1 or 0 is 1. And 1 and 1 is 1. Right? So now you're going to get 12 out of that back in binary. The other two operators, so the next one is not. So this is a unary operator instead of a binary operator because it just takes 1. So if you have, for example, if we not 12, so if we have not, or I'm sorry, it's not this one. That's the logic not. So the bitwise not is this symbol. So we have this, and then if you do 12, then that's going to give us, what is not 0? Not 0 is 1. Not 0 is 1. Not 1 is 0, not 1 is 0, right? So that's going to give us 3. So not 12 is 3. The last one is the exclusive OR. So we have, if we do like exclusive or between 8 and 12, then what that's going to give us is, so it's like the caret symbol. So 8 exclusive or and 12. So we'll have 0 exclusive or with 0.
Isn't the not 12, don't all of the zeros that should be
Oh,
also flip
you're right.
as well, so it
You're
should
right.
be -13?
Yeah. So yeah, I forgot about that. So implicitly, right, in C, you're going to have 32 bits. So when you not something, you're not just going to not the numbers that are like the binary digits that are used for that number. You also not every single 0 to a 1. That's all the way from wherever the last one is to 32. So yeah, let me draw that out real quick. I'll draw it over here. So it would be and then it would just be 0, 0, 1, 1. So this should be 28. Right, so there would be 28 ones.
So on the test, are we going to have to draw out all 32 ones? Or
I think you might, but I would assume that if you do something like this, or just say that they all, because I think it depends on what the question's asking, right? If it's asking like write out the 32-bit integer after you not it, then I would write all of them out. If it's saying what's the value of this, I believe it might be something like that, then I don't think you would necessarily have to.
Wouldn't it be 1 for this one, like 2 to the 31 minus 1 minus 2 to the third minus 2 to the second?
Say that again?
For the, like, writing it where you just do everything for 2 to a power of something,
Mm-hmm.
wouldn't you want the answer like that most likely?
Right. So because you can do it that way, like you were saying. You could do 2 to the whatever, and then just subtract out the 2 zeros. Yeah, and that's usually going to be the best way to do it. So like I was saying, if he's saying give me the value, right, you would do that. If he's saying give me the integer or the binary representation, you might want to write out all 28 ones and then 0, 0, 1, 1. It depends on the question. I think usually it'll be pretty clear, maybe even with an example or something like what's being looked for. So bitwise operators, a couple of uses. So like in the fox, goose, and bag of beans problem, the backtracking problem, you can represent your states with bitwise operators. So essentially what you would do is you would have, your 4 states. So you would start out with, put it down here. You would start out with 0, 0, 0, 0, right? And so if I draw the river here, you have like the fox. I don't know how to draw a fox. That looks more like a goose, so I'm going to do that. And then the farmer, the bag of beans, and then a fox is like, whatever. Okay, so it's like hieroglyphics. So they're all 4 on the one side, right? You could represent that as 0, 0, 0, 0. If you want to send one of them over, you flip that to a 1. And the way you do that is you exclusive or the current state with whatever integer, so if you wanted to change this bit right here, you could exclusive or it with 0, 1, 0, 0, right? So the integer representation for that would be 4. So you would exclusive or your state with 4, and that would flip the bit for let's say that this is the farmer, right? If you want to move the farmer, you exclusive or it with 4, and that's going to flip the bit. If you want to flip 2 at one time, you could exclusive or this with, you could change this to a 1. You'd exclusive or this with 4 plus 2. You'd exclusive or with 6.
the 8, the one example you didn't do with that exclusive or right there? That was right.
Which one? Oh, yeah. Exclusive or. So essentially the way that would work, if you exclusive or 8 with 12, what's exclusive or 0 and 0? Exclusive or 0, right? So it's going to be a 0. What's exclusive or 0 and 0? 0. Exclusive or 1 and 0. Now, what's exclusive or 1 and 1? 0. So that's the only difference. Exclusive or just doesn't count 1 and 1. 1 and 1 is not 1 with exclusive or 1 and 1 is 1. So essentially, it's exclusive. It has to be one but not the other, as opposed to either and both. So or is either and both. Exclusive or is one or the other, but not both. And then and is obviously both, and then not, you just flip the bits. So usually bitwise, bitmasks is what this is called, what we're doing here with the representation. And essentially what you're doing there is you're just saving space. If you need to represent lots of things and they have a binary state, that's what you want to use a bitmask for. So if you have two choices for like the state of many objects, you can use a bitmask for that. And then you just use the bitwise exclusive ORs to flip the bits back and forth depending on how your state is changing. Okay. Stacks and queues or wildcards? Oh, base conversion? Okay, so base conversion, let's see. So do you want to do like some number other than binary?
Yeah.
Or, okay. So let's say you have this number and you want to, and it's in base. You want to do 16? Okay, let's do. Okay, here. Well, let me change it then. Let's change this to a B. If we're going to do base 16. Okay, so essentially the way you're going to convert from this to decimal is you're going to take. It's the same thing you do with binary, except for you use powers of whatever your base is instead of powers of 2. So this is going to be 3 times 16 to the third plus 6 times 16 to the second plus 2 times 16 to the first plus b. So b is essentially,
Are we converting to base 10?
Yeah, so we're going to base 10 right now, and then we'll go from 10 to another base after that. Okay. So 3 times 16 to the third, 6 times 16 to the second, 2 times 16 to the first. B represents, so you stop at 9 usually, right? Yeah, so it represents 11 because when you start counting letters, you start at 10, so A is 10, and you count all the way up to 15 with F. So that's the way base 16 works, because you need 16 unique digits. 15 is F. Because it's 0 through 15 for 16 unique digits. So B is 11, so it'll be 11 times 16 to the 0. So, oh, okay, hold on. I need a calculator for this. I'm not doing that in my head. 16. Yeah, if anybody else has got a calculator, feel free to beat me. Okay, so it's going to be, oh, I guess I got to add it together, huh? Okay. So now, this is our number in base 10, right? So we went from 362B in base 16 to 13,867 in base 10. Now, if you want to, now even if you started with this problem and it said go from base 16 to base 8, for example, the way you would do it, well, with base 8 from 16 to 8, there would be the shortcut that we'll cover in a second. But from 16 to like 7, for example, you would need to go to 10 first, and from 10 to 7. I'm not aware of like a faster way to do that. I think you just have to go through 10, or through 10. So from to use the dividing method. So from 13,867, you would take that number, right? Is that? And you're going to divide it by whatever base you're trying to go to. So then, and then you put the remainder there. So if we divide, let's go to base 2 because that'll be kind of easier to do. Oh yeah. Want to go base 7? All right, so if we do 13,867 divided by 7, right? So what is that? What's the remainder? 13 is divided by 7. Oh, it divides evenly, okay. So that's 1,981 plus 0. And then that divided by 7, what? Wait, it divides evenly again. That's weird. So we have 1,981 divided by 7 is equal to 283 plus 0. Okay, so that doesn't divide evenly. So how do we do this? Okay, so 283 divided by 7. 7 goes in 40 times 280. So it's going to be with a remainder of 3. So it'll be 40 plus 3. And then from 40 divided by 7, we're going to have 20, 32, or 30, 35, plus 5. So we'll have 35 plus 5. No, not 35. 5 plus 5. Sorry. Right, because 5 times 7 is 35, plus 5 is 40. Okay. And then from there, we'll have 5, and then it'll go in 0 times with a remainder of 2, right? 5, yeah, with a remainder of 5, sorry. Okay, so now we're going to read these remainders this way, right? And that's going to be our representation in base 7. So we'll have, this is going to be 0, 1, 2, 3, 4. So we'll have 5 times 7 to the 4th plus 5 times 7 to the 3rd plus 3 times 7 to the 2nd plus, 3 times 7 to the 2nd plus 0 times 7 to the 1st plus 0 times 7 to the 0.
Won't the answer just be 55300?
Right, so the answer would be 55300. This is just how you would check. Right, sorry, yeah. So it will be, so the answer will just be 55300 in base 7. So 362b in base 16 is equal to 55300 in base 7.
What if the last remainder is 0? How would you write that? Do you just disregard 0?
Yeah, I would, yeah. I mean, you could write it, it could just be, but yeah, because it's going to end up not contributing to the value of the only reason you need the zeros on the right side is to know that they're shifted, right. Okay, let's do some wildcard stuff now. Or does anybody else want to do anything in particular? Oh, okay. Let's see. So let me look at this real quick to make sure I'm not lying to you before I do this. Okay. So, do you want to talk about converting to 2's complement, or?
Like if we have a number of 2's complement, like representing that within 2 to the powers.
Okay. So, I think the shortcut way to do it is if you have, for example, let's say you have like one, we'll do it with like 8 or 4-bit to make it a little bit easier, because it's the same concept, just with 2 to the 31 instead of 2 to the 3rd, so, or 2 to the 4th, or yeah, 2 to the 3rd. So if you have 1, 0, 0, 0, right, then essentially instead of being, when this first bit is 1, it's you subtract 2 to the power that that bit represents, correct? So, for example, in this 4-bit example, instead of this being positive 8, it's negative 8 because you're subtracting from the rest of it, which is 0, you're subtracting 2 to the third. So this one will be equal to negative 8. So then if you put 1, 0, 0, 0, 1, or 1, 0, 0, 1, right? You're going to subtract 1 from that, so it'll be negative 7. So it'd be negative 8 minus, or 1 minus negative 8, or minus 8. So it'll be negative 7. Now if you have, let's say you have 0 here, right, and then you have 1, 1, 1, you just do it like regular binary. So you have a 0 here, and then you have here, you have 4 plus 2 plus 1, so it'll be 7. So the range that you have with 2's complement is always 1 more in the negative direction than it is in the positive. And what the reason, essentially what this eliminates is just having 2 types of 0. Because otherwise, if you did negative 7 to positive 7, you'd have 2 representations of 0. So that's pretty much it. You just, if you expand it to 32 bits, you're going to have 2 to the 30, excuse me, 2 to the 31 subtracted from whatever your number is. But that's essentially the way it works. So you're going to have, so on your range, you're always going to have, if you have 32 bits, your range is going to be negative 2 to the 31 to 2 to the 31 minus 1. Does that make sense? Everybody follow me? Okay. So let's do complement. We can move on to wildcard stuff. I'll try. I brought like all of them. I printed them out, but I'm probably just going to pick like some of them that are a little more interesting. Okay. So this one, and for those of you, I don't know if any of you are who are in Dr. McAlpin's class. These are from Dr. Simlansky's class, but they're pretty good, like general overviews of different concepts, like conceptual thinking, and then they'll also probably be very similar things on the foundation exam for those of you who are CS majors. So for this one, it's a lot of words, a lot of stuff, but essentially what it's asking is a computer scientist made a hash function and he wants to test how good it is. So what he does is he sets up this code here and he tries to figure out how many collisions he has, and he gets the number 0.06. And then the question is asking, if you look at this code, what's wrong with his conclusion? So it says if there's nothing wrong, write a haiku, that the haiku will be graded based on creativity. So obviously that's probably not the answer. There probably is something wrong with it. That's probably a big hint. So looking at this, usually, at first glance, like there's nothing syntactically wrong with it. There's nothing wrong with the approach, except for the fact that when he does his calculations, right, what he's trying to test is whether or not it's a good hash function, but what he's actually testing is how many collisions there are. So that's like kind of the key problem with this is just because there's not a lot of collisions doesn't mean it's a good hash function. Because what if you put the same string in twice and it gives you 2 different numbers? That wouldn't necessarily increase the number of collisions, but that would be an absolutely terrible hash function because you'd never be able to retrieve any of your data because it would go to the wrong hash values. Other than that, he's also doing his insertions. This is kind of like a nitpicky thing, which would not probably be like the best only answer that you would put, but when the data that he's using is random values on the range of like int max. So he's not testing negative hash values, or not hash values, but he's not testing negative inputs to your hash function. And he's also not testing like real data in the sense that like it's unlikely that you would ever have a data set where it was just random values from 0 to int max. But those are kind of not, the best answer is definitely that he's not checking to see anything about the hash function other than how many collisions it has. Let's see. So this one, we'll skip this one because for everybody in Dr. Simlansky's class did this for your homework. Okay. So this one says, suppose you have a corpus file that contains one sentence per line. Some of the sentences might be repeated at various points throughout the file, and you're interested in creating a new copy of the corpus, where each unique sentence occurs exactly once, no repeats. Here's the catch. Since the corpus, or suppose the corpus is huge, several gigs, so you can't fit all the sentences into memory at once. Even if you were to use a try, However, you have virtually unlimited hard disk space available to you for reading and writing. How could you write a program in C that would ultimately create a new copy of the corpus where each sentence occurs exactly once? So usually I think the way that you would approach this would be, if you're trying to figure out, like essentially the problem breaks down to, you cannot store all the words to check to see which words you've looked up previously, but you need to know which words you've seen before, or sentences, because you're trying to only store each sentence once. So if you hit, I like pie, and then the next sentence is something else, and then you see I like pie again, you want to know you've already seen I like pie without storing I like pie, because you can't fit all the sentences in there. So you need to go one sentence at a time, somehow keep track of the ones that you've seen, but in a way that's much less memory intensive as it would be if you were just storing all of them. So usually whenever you're trying to just know if something's happened or not, usually like the computer science concept would be like a flag, right? Like you want to set a flag to know whether or not you've seen a certain thing before. The other thing is you want it to be as fast as possible, right? So if you want to look up a flag and you want to store the sentence without actually storing the sentence. So I think that probably the best data structure for this, and this is probably like the best data structure for like 90% of problems, is a hash table, right? Because you can hash strings and you can get a value for it, but you're not going to necessarily have to. Now, you probably ideally would store the string with the hash value so that you can make sure that you didn't have an improper collision, but you could set it up to where you had a hash table that was bigger than the number of strings that are in your corpus, because that would still be much smaller. Like if you stored just a single binary like Boolean or something for 0 or 1, you could have a hash table that was big enough to fit one single Boolean for every sentence. So what you would end up doing is you'd hash it, you'd go to that location, and then you would check to see whether you've seen it or not. If you've seen it, you write it to the new file. If you haven't seen it, you write it to the new file. If you have, just skip, go to the next word or next sentence. Yeah, so that one's pretty easy. Let's see. I think that might be it. So, okay, questions? Anything at all from anyone, any topic? I guess we can go back and do stacks and queues if anybody's interested in that. Okay. Let's see. Okay, so in terms of stacks and queues, essentially they're two related data structures that just depend on what you need in terms of your data. So a stack is usually represented like this. It's like a vertical array. So when you put something in the stack, let's say you're going to put like 10 in the stack, right? You put 10 in, okay? Then if you want to put something else in, you put it on top. So let's say you put like 15, and you put 17 in. Now the operation that you're going to use to put things on the stack is called push. So this is just terminology. So you push things onto the stack, right? And then the only supported operation in terms of deletion or removal is pop. So when you pop something, you always pop what's on top of the stack. So if we pop, right, you just take the element that's on top. And then a related operation to that is peek. So peek essentially does the same thing as pop, except for it doesn't actually remove the element, it just returns the value that's there. So pop actually takes it off and returns the value. Peek just looks. Then the other ones that are usually there is empty. So that checks if your stack is empty or not. That's usually useful for stuff like if you're doing operations with the stack and you have like a while loop, you might want to like stop your operation if it's empty, whenever it becomes empty. So this is called a first in, last out. So Philo data structure, first in, because the first element that goes in, right, if you insert 20 elements, and then you pop all of them, you push 20 and then pop 20, the first one that was pushed is going to be the last one that was popped, right? So first in, last out. It's useful for a lot of things, including like simulating recursion. So if you guys see something on your final where it's like, oh, you know, do something, and usually you do it with recursion, it's like, but don't use recursion, it's probably going to be using a stack to simulate that recursion. So yeah, that's a stack. You can implement it two different ways. You can implement it with an array or with a linked list. It just kind of depends on what you want to do. Runtime-wise, if you set your linked list up properly, you can get order 1, depending on if you have tail and head pointers and whether or not it's, you know, just depending on that stuff. Whether you're pushing and popping, or whether you're inserting or removing from the tail or the head as well. Your runtimes there. Now, if we look at queues, queues are usually just represented like this, as a sideways array. So in contrast to the first one, queues are first in, first out, first in, first out. And so this is stack. And this is going to be, so the queue is first in, first out. So for example, if I put in like, you know, 10, 15, 17 again, right? The operation for this is going to be in queue. So it's N, Q, U, E, U, E. And then when you want to remove something, it's DQ. So it's DE, Q, U, E, U, E, right? So when you want to DQ something, instead of taking 17 like it did in the stack, it's going to take 10. And then it's just going to move to 15. So these can also be represented with both a linked list or an array. And again, it just depends on what you're trying to do, whether you want to involve the linked list or not. The other two operations, again, you can have peek, which will just look at what's at the front. And then you also obviously would have is empty, so you can know if your queue is empty. In terms of runtimes, with an array, as long as you're keeping track of like where the top of the stack is or like where the front of the queue is as you remove things, it's going to be order 1 usually. Well, actually, with an array, unless you're very clever, the queue is going to be order n when you remove something, right? Because if you have like these elements in your queue, when you remove 13, right, you would need to shift all of these over 1 to get them at the beginning, unless instead of doing that, you keep track of your head of your queue by just moving it over. And then what you would do is, like, for example, this array, let's say it's full, right? So let's say you remove 13. Now what you would do is when you go down here to 10, you go, oh, I can't insert anything off the end. So you would just move it back over here and insert in the empty spot at the thing. So it would almost be like it would revolve around, right? So you would keep track of where the head is, and then everything past the head all the way up to the head, even if you loop back around, like if you just mod by, you would just keep checking if you've reached the head yet. And if you haven't reached the head yet, you just keep going back through the beginning and inserting things. So that's how you could get order 1s out of your queues with arrays. With linked list, it's just going to be, let's see, it's going to be if you insert at the head. Or no, but you can insert it, yeah, you can insert at the head and then remove at the head as well. And then what you're going to get is, so that would be for a stack, because what would end up happening is if you insert at the head, right, you'll get something like this, where this was the head, right? So then if you insert at the head, you're going to get another element like this. Now this is the head. So whatever element was inserted last will be the first thing that you pop. Like if you push here at the head, this was the head, you pushed here, and then this was the head and you pushed here. Now if you pop the head, you're going to pop this thing, which was the last thing to be popped. So that would be, with linked lists, order 1 for a stack. Now for a queue, if you're going to do linked lists, you want to get the, what do you want to do? Oh, yeah, you can push at the tail and pop at the head. So if you have your linked list like this, right? If you have one element, so you push at the tail. So this was the first element in here, so I'm just, right, it was the first element. You push the second element in, okay? You push the third element in. So these are, the numbers represent in terms of the order that they were entered or enqueued. So then when you want to remove something, if you remove from the head, obviously removing it from the head of a linked list is order 1. You should just go to the head, move the head over 1, and that's it. So if you want to remove it, this was the first thing that was in, so now it's the first thing out. So that's how you would do it with linked list with a queue. Yeah, I think that's everything. Is there anything else? Anybody? Okay. Let's see. So this is going to be kind of tough because it's hard to come, like I was trying to, before we started this, I was trying to come up with some problems, but it's really difficult to come up with things that you guys haven't already seen that aren't like way. So honestly, in terms of backtracking, if there is a question either on your finals or on the foundation exam, it's probably going to be in terms of fill in the blanks. It's not going to be like write a backtracking function because that would be a little crazy. So we can talk about, let's see. We can talk about like the pieces of the backtracking function.
What about like the anatomy?
Yeah, that's what the anatomy of it. I'm just gonna look real quick to make sure I get the terminology that he uses right. So I think. Okay, so usually you would have, a backtracking problem is usually one that involves recursion, right? But it also involves choices. So for example, with the maze solving problem, you know, if you have like this maze and like these are, and like this is your path out, so I'm just gonna surround these. Maybe you tried going this way and this was a dead end, right? And then, you know, you go this way and you come out and this is the exit here. So these are all dead ends. So essentially, at every step, right, you want to have multiple choices that you can make where you're changing states. So the important part is that you need to have base cases, right? You need to have base cases that check for not only states that have, you need to check for states that have already been seen and states that are failures, right? Then you want to have a for loop where you make your choices, you make your changes of states, and then after you've changed your state, so like let's say, you know, you're right here and you try to go left, okay? That's a failure. So when you come back from that recursive call, you need to reset your state to whatever you were right here. Because when you change your state to be right here, you don't want to then try the next move from that state. Does that make sense? So like, let me try to draw it better, hold on. So if you're here, let's say you're here, right? I'll draw it a little bigger. You try this direction, okay? So when you try this direction, you actually move to right here, like to where the dot is. When you, let's say that this is a failure, okay? You come back, you need to reset the state to being on this X. Because otherwise, when you make your next try, let's say you're going to try left next, you'll try left from here, not left from here. So you need to, every time you make a call, when you return, you make sure that your state is reset to what it is from the duration of the function. Right. Now, if you succeed, well, either way, because it depends on the type of backtracking function you're doing. So if you're, for example, if you're trying to do like the backtracking function where he prints like the n queens, right? He prints all of the solutions. You would still want to go back because you wouldn't want to try and see if you could move a queen. You know what I'm saying? Like you might skip a position of a queen because you would just put it straight across instead of putting it. You might skip some queens if you do it like that. So yeah, you always want to reset the state, whether or not it's successful or not, because you're trying something new from where you were before, right? You're backtracking. The back part is the resetting of the state. So you want to have your base cases, right? They got to check for So the important parts, right, is you have your base cases. So base cases that check for duplicate states and invalid states. And the second thing you want to do is make choices and reset state after each choice. And then the last thing you need to do is you need to decide whether or not your goal is to end after one or maybe a couple solutions, or if you want all the solutions, and then you need to keep track of that as well. So some things I would say as far as problems possibly on the final or the foundation exam would be, usually it'll be something like they'll have most of the backtracking function written out, and then it'll have some fill in the blanks, right? So you're going to want to try to understand what they're trying to do, right? So you're going to want to understand what mechanism is representing the state. So for example, with the n queens, it's the array that represents the position, okay? With the fox goose, the bag of beans, it's either the string or the bit mask or whatever. But you need to understand what the thing is that's representing your states, where the mechanism for changing the states is, and then you want to make sure, it's usually going to have a problem with it or something like that. You want to try to understand, like, okay, so I'm at this state. These are the 4 things that it's trying to do. Why is it not working, or what does it need to do? It needs to know this data, this variable. It needs to have this updated, that kind of stuff, right? So you want to try to understand it in terms of that. So you want to look at the base cases first, I would say, and then understand, like, what are the terminating conditions? What's the goal, right? Where's the end? Where's your end of your, like, where are you trying to get to? How is it making the choices, right? So like, okay, maybe it's an array that goes 4 directions like a maze, or maybe it goes 2 directions because there's only 2 possible choices at every step, or something like that. And then knowing how the states are stored and how it's examined. So like, for example, in the n queens problem, he passes the state to all the queens are safe, right? And he never showed that to you guys, I don't think, right? Because it's the first problem that he does in CS2, is write all the queens are safe. So it's not, so essentially, like, you want to know each individual step of it, right? So you start out with your base cases, then you look, okay, he's making these choices. This is the representation of the state, all right? Pass that to whatever function or process is checking the state. So you want to, those are like the major parts that are either going to have an error or that you need to understand well enough to fill in what variables go where, kind of thing. Okay, we have about 10 minutes left, 15, somewhere between there. So anybody else got any questions? Anything? Last minute clarifications? Okay. We can put this, I'll put this QR code up here for the survey to tell us how you, tell us how you really feel. There you go. If anybody would like to. How does that work? So there's some papers on your tables too that have like the QR code. So I think you just scan it and tell us how it went. Yeah. Okay, I guess I'll hang up here if anybody thinks of anything. Otherwise, I think that's it.
The session tomorrow, I know it's in the morning. Is there one later or no?
I'm not sure.
I think it's just one tomorrow.
It should be, I can look if anybody's interested on the schedule.
6:30.
Okay. Okay. Yeah, I think,
This one at 6:30.
Today though.
Yeah.
Oh, okay.
okay.